Control engineering has a single, unforgiving objective: to force a physical dynamic system to achieve a desired state, even when external disturbances and unmodeled physics act against it. We can contrast that chaos with modern implementations, like an atmospheric adaptive UAV, executing precise, stable maneuvers in turbulent air. Achieving that level of stability introduces a strict architectural tension. Engineers must balance heavy algorithmic computation against the rigid, deterministic timing constraints of the physical hardware attempting to execute those calculations. Classical simple algorithms excel at basic regulation, but they fail when a system scales in multivariable complexity or is pushed to the edge of its physical limits. To understand how engineers solve specific physical failures, we have to trace the architectural evolution of these systems, from basic timers and classical regulators, through predictive optimization, up to modern physics-informed neural networks. Modern control theory serves as a structured engineering response to the escalating complexity of the physical world, prioritizing functional stability over abstract mathematical elegance. We can establish the simplest control paradigm using an automated water-level rig. In an open-loop architecture, the controller issues commands based strictly on a predefined schedule or timer. It turns a pump on for 10 seconds, assumes the tank is full, and turns it off. That architecture fails immediately if we introduce a completely unpredicted disturbance. If the tank develops a leak, the open-loop controller will continue running its 10-second timer, blind to the fact that the water level is dropping. In a closed-loop architecture, the system feeds the measured water level back to compare against a target set point. A PID regulator uses this error to continuously correct the valve. The resulting performance graph shows a fast rise time, modest overshoot, and low steady-state error. The primary advantage of a PID regulator is that it delivers these exact performance trade-offs at a low computational cost, making it viable for nearly any embedded hardware. However, PID has a strict architectural limit. It is entirely reactive. It breaks down when managing industrial processes that involve multiple interacting variables and rigid physical constraints that cannot be violated. Managing interacting variables while respecting strict constraints is a predictive problem, not a reactive one. Solving it requires a completely different mathematical approach. In an industrial fractionation plant, the environment consists of highly coupled, multi-column systems, where adjusting the temperature inherently alters the pressure. To manage these interactions natively, engineers deploy Model Predictive Control, or MPC. The MPC controller utilizes an internal mathematical model to simulate its future outputs over a prediction horizon. It solves an optimization problem at every time step, calculating a trajectory that actively navigates toward the set point while completely avoiding hard constraint boundaries. In high dynamics applications, this predictive capability provides a distinct advantage over PID. Simulation tests of onboard attitude determination systems show that an MPC architecture halts unwanted rotation substantially faster than classical regulation. That speed and precision require high computational power. Solving continuous optimization matrices demands significantly more hardware resources than a lightweight classical error equation. MPC trades computational resources for the ability to anticipate multivariable interactions and mathematically avoid system limits before they physically occur. Certain multivariable mechanical environments, like high-speed robotic manipulation, experience continuous wear, tear, and external friction, making exact physical modeling impossible. Predictive control frameworks are vulnerable when their internal process models contain unmodeled dynamics or severe uncertainties. If the map is wrong, the prediction is useless. When exact models are impossible to build, engineers rely on robust optimal frameworks. Techniques like the linear quadratic regulator, or LQR, are designed to synthesize controller gains that maintain performance despite these unknowns. Specific model-free schemes, such as adaptive dynamic programming, permit the controller to continuously adjust its internal gains online without requiring a detailed mathematical map of the physical plant. This adaptive feedback allows real-time embedded systems, even spatially distributed ones, to approximate and reject external disturbances locally without requiring central coordination. Robust control theory shifts the engineering focus. Rather than perfectly modeling an unpredictable world, The goal is designing mathematically guaranteed stability boundaries that hold true regardless of the chaos inside them. Some environments present severe, unpredictable nonlinearities, such as an electric vehicle's steering system suddenly hitting a patch of ice. To force highly nonlinear systems into compliance, engineers utilize a geometric method known as sliding mode control, or SMC. This 3D phase plane graph illustrates the mechanism. The controller forces the system's erratic state trajectory onto a predefined, mathematically stable surface. Once there, it slides directly toward the target state. While locked onto this sliding surface, the system is immune to disturbances. But zooming in on the trajectory reveals a violent, jagged sawtooth wave oscillating rapidly, a severe physical drawback known as chattering. To prevent chattering from tearing physical hardware apart, practical implementations require boundary layer smoothing or hybrid fuzzy logic strategies that maintain the trajectory while reducing actuator wear. Geometric control methods can guarantee robustness against extreme chaos, but they exact a heavy toll on physical actuators unless the mathematics are carefully mitigated. At modern industrial scales, no single control philosophy is sufficient. Robust tracking, predictive constraints, and fast error correction must be fused into hybrid architectures. This hierarchical block diagram shows how cascaded systems operate in practice. A meta-heuristic optimization algorithm sits at the supervisory level, calculating exact tuning parameters. This allows a slower, intelligent algorithm to supply gains to the fast, classical PID loops below it, which then rapidly eliminate residual oscillations in hardware, like heavy crane operations. When first principles physical models are incomplete, controllers increasingly incorporate deep reinforcement learning and neural networks to manage the uncertainty. However, these data-driven methods face severe integration challenges. Real-time control requires deterministic latency. An algorithm cannot pause to compute while a robotic arm is swinging. The computational burden and strict certification roadblocks prevent easy deployment. Achieving ultra-low latency, closed-loop AI control relies directly on edge AI hardware maturity. Local inference capabilities and failover reliability are the primary bottlenecks dictating whether these systems can function safely on the factory floor. Utilizing physics-informed learning increases a system's resilience to environmental uncertainty, but also raises the validation and testing burden required to prove it is safe. Whether implementing a basic timer or a physics-informed neural network, successful control system design relies on a strict engineering discipline, matching the mathematical ambition of the algorithm to the rigid physical determinism of the hardware.